Matlab function no to A, and then each column construct, all the columns construct the basic set of solution of the original equation. Let me demonstrate this part by an example. It might be easier to understand. Suppose we have a linear equation like this. How can we solve it? To solve the equation, we have first to enter the equations into Matlab environment A and B. So if you are trying to solve it in this way, you will get errors. Since A is not invertible, rank of A equals to 2. So now we have to check what is the rank of the matrix C. Rank C can be obtained by this command. And it is seen that the rank of C is also 2. They are the same. So we say that this equation has infinite number of solutions. So how can we get the basic set of solutions? X equals to NULL, we try to use symbolic computation. So we can have a 2-column matrix here. And these 2 columns are X1 and X2 of the basic set of solutions. So now we can assume 2 constants, A1 and A2. Then we can have X1 equals to A1 times X, the first column, plus A2 times X, the second column, and we can construct an infinite set of solutions. No matter how we select A1 and A2, it is a solution to the homogeneous equation, so we can check A times X1, we will see that it satisfies the homogeneous equation, no matter how we select A1 and A2. And how we can find X node satisfy the original equation? X node equals PIND A times B. It better changes to symbolic result. And X node is can be obtained like this, so we can verify it. And we can see that X node does satisfy the original equation. So the general equation now is X1 plus X node. So this is the general solution to the original problem, no matter how you select A1 and A2. So let's check it. So in this way, you can find the infinite number of solutions of original linear algebraic equation. So we have completed the 2 cases. One is when it has unique solution. The other one is when it has infinite number of solutions. And how can we get it? So the last question is when the original equation has no solutions. You can still construct a testing matrix C. And if the rank of A is different from the rank of C, we say that the matrix itself is a conflict equation. There isn't any solution in the equation. So if this condition held, then we say that there isn't any solution to the original problem. And sometimes we can use the Mertel's generalized inverse to solve the original problem. That means to minimize the error in the equation. there isn't a solution, but we can find a x which minimizes error. The error will not be zero, but it is minimized. So we can use a command like this to find the least square solution of the original problem. Here is an example, and we change the right-hand side of the solution in the previous example, and we will see that the matrix, the Rank matrix C is 3, and the matrix Rank matrix A is 2. So they are different. So the original equation is a complex equation. There shouldn't be any solution, but we can try we can try the pseudo inverse of A times B. We can get the least square solution. So this is the error, the norm of the error. This is the smallest norm we can get, and this is the solution. We call it least square solution. So let's check what is the solution. For this particular example, we see that two of the equations hold for the x will okay, but for the other two, we have errors. However, these errors are minimized. And this kind of solution is particularly useful in data digging, where we have quite a lot of measurement data, and we have only very few variables, and for something like this, we have quite a lot of data testing. And in each question, in each equation, there might be a reminder or residue of the error in each term. So, for instance, we have 4 parameters to be determined, and in our experiment we found around 10 sets of data. Then we may find the solution to this kind of problem with the error minimized. So this kind of solution is useful in engineering fields, and in particular data digging fields. If we consider an equation, linear algebra equation like this, we can take transpose to the equation, and we can convert it into this form, which is the same as the one we discussed earlier. So then you can follow the strategies later on to find the solution to this equation. So any questions to this part? We'll have to do it here. Understand all that? For the decomposition part, just ignore it if you are not happy with it. Unless you have to do it on purpose for some particular tasks, we do not have to use them. For computation, for solve these solutions, can be useful. Any questions? We should have a great year.